The two graphs we explored last lesson were the y equals sine x and y equals cosine x trig functions. And these are what's considered like the basic ones. A bit like y equals x squared, the parabola there is the basic parabola. And then what we do is we start to play with these particular trig functions or trig equations. Now let's just go through and sketch them again just to jog our memory of how it worked. Right, so remember what we do is we consider how long it takes to do one complete cycle, which is 2 pi. And then what we do is we split the complete cycle into 4 separate parts, which is 2 pi on 4, which is pi on 2. And this thing here we call this a scale. That shows you or helps you mark in your Cartesian plane. Pi on 9, what am I doing? Pi on 2. And then we go up in increments of pi on 2, a bit like, again, if you're marking a Cartesian scale, you go 1, 2, 3. This time we're going up in pi on 2s or 90 degrees. So this would be pi, this would be 3 pi on 2, and this would be 2 pi. Now remember, what we do then is consider the unit circle and know that sine of 0, the y value there is 0, and then recall that it maxes at 1, mins at -1. So at 90 degrees, we get 1. At 180 degrees, we go back to 0. At 270, we go down to -1. And at 2 pi, or back to 0 again, we're at 2 pi. And we just complete it for the values in between. We get that shape there, noting that it continues indefinitely for all values of x. Right, this one here, let's do y equals cosine x or cosine theta, whatever that variable is. It's x in this case. All right, so cosine takes 2 pi to repeat itself. Again, to get the scale, what we do is we split the cycle length into 4 separate parts, which we again get pi on 2. There is pi on 2, pi, 3 pi on 2, and 2 pi. Okay, so now what we would do is to visualize how cosine works. We start at 0 and note that cosine at 0 is actually 1. The x value there is 1, so cosine starts there. Up here, the x value is 0. Back down here, the x value is -1. Back to 0 again, and back to 1, up to there. So we get this way. Not bad. We get that particular graph, noting that it continues indefinitely for all values of x. Right, so left you with this question here, what is the highest and lowest y value produced by both graphs? So max is 1, okay, so we get the highest value is 1, and min is -1. So here is the graph of y equals 2 sine x. Right, now what you might note here is have a look at the maximum value produced by this one, the highest and lowest y value produced. The max is 2 and the min is -2. We can see that down there. Okay, and our max value is on this bump here, that's 2. And remember, this just repeats itself after that. So we'll just get another form of this. So those of you thinking, oh, doesn't this or might this go higher? No, we'll just get one more repetition of that. That will max at 2 and min at -2. The value from the center line of the graph to the highest or lowest point is called the amplitude. Okay, so when we're talking about the amplitude, this line here is called the center line of a trig function. And the distance from this line, or the value, the distance to the max or the min, which in these two cases here is 2 and 2, we call this the amplitude. Okay, I refer to it often as the amp for short, okay, the amp of the trig function. Let's go back to this one here, and we'll note that cosine x, that value there is 1 before the cosine, and sine, the value is 1. And note the max and the min values, 1 and -1. 1 and -1 for this graph here. Right, so what you might note is this value here is 2, which produces an amplitude 2, or a distance from the middle line here of 2 and 2. Okay, so this value here, we look at that, and whether it's negative or positive, we just state the positive version of the value. So if that was -2, I would still say the amplitude is 2. All right, so let's have a look at a couple of examples. What is the amplitude of 3 cosine x? Well, the amp is 3. And we'll show you that graphically. So here comes a trig function. So this is y equals 3 cosine x. And notice that the highest value is 3, the lowest value is -3. All right, what about this one? So just being a little bit tricky here, this one here is 2 over 3 times the sine of x. I can rewrite it like that. Therefore, the sine of x has been multiplied by 2/3, so the amplitude is going to be 2/3. This one here, tempting to write -3, the coefficient value, but actually it's always the positive version. So we ignore that negative sign and we say the amp is 3 for that one as well. Okay, and I'll just show you again that one. So if I put a negative sign out the front of this, what it will do is actually reflect it in the x-axis, which produces a different graph, but will still max and min at 3 and -3 respectively. So the amplitude is still 3, but the graph is a reflection. All right, notice how the graph of y equals sine x and y equals cosine x repeats every 2 pi. That's called the period. So when it repeats itself, that's, or how long it takes to repeat itself, is the period. And what we can do is change the period. Okay, and so I might want something, just say I'm modeling something that has a longer or a shorter period. All right, here comes another one. So what I can do is, if I graph y equals sine, and I'm just going to put a parameter in here, sine AX. And what I'm going to do is vary this value. So this value here at the moment is 1. If I increase it to 2, what you'll notice that happens is it repeats itself more often, or if it's between 0 and 1, less often. So depending on what I'm trying to model, I can just adjust this value here to change how often it takes to repeat itself. All right, now let's have a look at this graph here. We've got the graph of y equals 2 sine of 2x. What's the difference between y equals sine x, which has a period of 2 pi, and y equals sine of 2x? Well, let's have a look at how often this repeats itself. It's actually repeating itself every pi. So the period of this one is pi. Okay, so, well, not so. Sine 2x has a period of pi versus sine x, which has a period of 2 pi. All right, so intuitively, you might think that by slamming a 2 value there, that what that will do is that will basically double the amount of repetitions, but it actually works a little bit counterintuitive. So here's how we work out the period for any trigonometric function. So how do you work it out? If this is our equation, y equals sine n times x, calculate the period, consider the standard period for sine x, which is 2 pi. So I go, okay, 2 pi, and then divide it by whatever this value here is. In this case, or in the graph above, it was 2. So what I would do for this one, here I've done the calculation, n was equal to 2 for this graph here. So I do 2 pi over 2, which means it's pi. So the period in this case was pi. Let's do another couple of period checks. Right, so this one here, we have an n value of 3. And so what that means is it's going to repeat itself 2 pi on n or 2 pi on 3. So one period is going to take 2 pi on 3 units of time as opposed to the standard 2 pi. This one here, we have an n value of a half. So we've got 2 pi over a half. How many times can I squeeze a half into 2 pi? The answer is 4 pi. So this one here, a half, when I've got that, what that's going to do is actually stretch the function out. The period now is 4 pi. It takes much longer to repeat itself. All right, this one here is a little bit of a trick one here. N value is pi on 4. Okay, so what we're going to do is 2 pi over pi on 4, which is 2 pi divided by pi on 4, which is 2 pi times 4 over pi. The pi's cancel out, means the period is 8. And so what we can do is get trig functions to actually produce standard kind of numbers rather than radians, still radians, but instead of these sort of values here, we can get them to actually mark the Cartesian plane without pi's in our numbers. All right, so let's put it together and actually draw some of these graphs. So here's our first one here, and what we'll do is note that the amplitude of this function is 3. Our period is going to be the standard 2 pi for a cosine function over the n value, which is a half, which is 4 pi. Now what we're going to do is get our scale. So the way we get our scale, this is how we're going to mark the Cartesian plane, is we take the period and we split it into 4 parts. 4 pi on 4 is pi. Right, so that means that to draw one cycle, and this asks for one positive cycle, we're going to have 4 key points. Okay, sort of 5 actually, but let's just do that. So we've got pi, 2 pi, 3 pi, 4 pi. All right, so we've got 1, 2, 3, 4, 5 key points. All right, now what I do is I think about the basic shape of the cosine graph. Okay, now where does cosine start? It starts at +1, but in this case here, instead of starting at +1 on the basic, this one is going to start all the way up at 3. Then cosine at the next phase of it, it'll drop down to this here, this point here at pi, then it will drop down to here, here, and here, and it follows the same shape as the standard y equals cosine x graph. So I consider how that would look and just place it on the points that get given to me. And notice when I draw this, I'm going to draw it again now. Oh dear. Right, we've got one complete cycle, okay, and how long does that take? It takes 4 pi to do, which we stated as our period. Now, this is the center line of the function along this line here. Let's look at the difference between the center line and the max and the minimum. The value is 3 units up or 3 units down. The amplitude is 3. So everything's looking correct for this sketch. It asks for one positive cycle only. If it asks for more, we would just continue it. All right, one positive cycle of this graph here. So let's note that our amplitude is equal to 2. Okay, that's that value there. So it means it's going to go up and down 2 units from the origin. All right, our period for a standard sine function is 2 pi, and we're going to divide it by this n value here, which is 3. Right, let's get our scale. So that's 2 pi on 3 on 4. Okay, so what that's going to mean is I'm doing 2 pi on 3 divided by 4, which is 2 pi on 3 times 1 over 4, which is 2 pi on 12. Now 2 pi on 12 is the same as pi on 6. So let's start marking. I've got pi on 6, 2 pi on 6, which is pi on 3, 3 pi on 6, which is pi on 2, and 4 pi on 6, which would go here, which is 2 pi on 3. Notice when I've made my 4 markings here, including the 5th for the starting point there, I've got to the end of the period. All right, so 4 markings should get me one full cycle. Now what I do is I think about the basic sine graph. which starts there, goes up, down, down, up. Okay, we'll take that shape there. And I simply do the same thing, except I use this scale to sketch it. So I start at the origin, go up to there, down to there, down to there, and back to there. Complete the sketch. And we've got one positive cycle of this graph here. All right, let's just double check our work. So our period, or one cycle, takes 2 pi on 3, which matches that. Here is our center line of the graph here, and we go up 2, down 2, so it matches the amplitude there. So big tick. All right, what about the graph of y equals negative 2 sine 2x? So what do you think the negative does? Okay, consider the graph of y equals x squared and y equals negative x squared. What it does is it takes these y values here and negates them, okay? And what happens is you get a reflection in the x-axis, okay? So this negative sign is a reflection in x-axis. All right, so let's sketch one positive cycle of this particular graph here. Now we go through the same basic process. The amplitude is 2. The period is 2 pi over the n value, which is 2. So period is pi. Our scale is the period split 4 ways. All right, so let's label our scale. So we've got pi on 4, 2 pi on 4, which is pi on 2, 3 pi on 4, and it's always a really good thing when you get to the 4th marker point and you've hit what you know is the period. Right, our amplitude is 2, which means the function will max out at positive 2 and get its min at negative 2. Now, our typical sine graph, we saw that before, goes like this. But what this negative sign does is it'll basically negate all of these y values. So these positive y values here, these ones up here, will have a negative sign plonked in front of them. And what that will yield is this section here will actually be reflected in the x-axis, just like this graph here, the parabola. This was the positive, this was the negative version of it. Okay, that got reflected in the x-axis. The same exact thing will happen here. Now these ones here that are negative already, what that will do is when we plonk a negative sign in front of those negative y values, it will actually put it up there. So a new graph will actually look like this. That's the behavior that it will have. So what it will do is it will start at the origin, and instead of going up, it's going to come down. And then it will go back up again. That's what we get. Is a graph that looks very similar to the standard, except everything gets reflected in the x-axis. All right, so there'll be an exercise. It's 4K, and there'll be another worksheet on top of that.